In Chapter 26, we're continuing on what we did in the second half of Chapter 3. So in the second half of Chapter 3, remember we were working with one kind of data, and that kind of data was categorical. And we're continuing that with Chapter 26. So we'll only be working with data like smoker, non-smoker, employed, unemployed, that sort of thing. We're working with groups, with categories. And we'll be using the chi-square test. The chi-square test. The symbol for chi-square is that, and it's pronounced with a hard K sound, chi-square, chi-square. There are actually two chi-square tests. The first one is the goodness of fit test. That's where we have one categorical variable, and then we'll talk about the regular old chi-square test where we have two categorical variables. If you remember, when we talked about inference before, we had a choice of confidence intervals or hypothesis testing. Inference, of course, is drawing conclusions about the entire population from a sample. So that's what we're going to be doing in Chapter 26. Chapter 3 was all about describing what we've got in our sample. Chapter 26 is saying, okay, that's what you saw in your sample. Based on that, what do you think is true in the population? So with inference, we have a choice of confidence intervals and hypothesis testing. Confidence intervals to estimate something in the population. What is the true mean of the population? How big is the difference in percents in the population? And hypothesis testing, is there a difference? Is the mean equal to 10? Answering a yes-no question about what's true in the population. So the only kind of inference we'll be doing in Chapter 26 is hypothesis testing. So we'll be using the same four-step procedure as before: hypotheses, test statistic, p-value, decision. The hypotheses, remember, are always about the population. What's true in the population? We're making a claim about what's true in the population, and then we'll collect sample data to see if that supports our claim about what's true in the population. So we'll start with hypotheses, a claim about the population, and the null is always that there is nothing going on, no difference, no association. There is nothing going on here. No difference. It's the way it's always been. And then the alternate is that there is something going on. There is a difference. There is an association. So that's also true for this hypothesis testing that we'll be doing here. The null hypothesis for goodness of fit will be there is goodness of fit. The percent we see in a category is exactly what we expected. And the null hypothesis for chi-square is there is no association between these two categorical variables. And then the alternate is there is some sort of a difference, or there is some sort of association. The chi-square statistic takes 1.5 years to compute, so we will never compute it by hand. We will always let the computer do it for us. But it's like all of our other test statistics. The test statistics are always a measure of how our sample matched up with our null hypothesis. And the chi-square statistic is no different. That's what it looks like. What we're going to do is we're going to take what we observed in our sample, this count that we saw in a certain category or combination of categories. We're going to subtract off what we expected to see, the count we would have expected to see if the null hypothesis was true. So how does what we observed in our sample compare to what we would have expected to see if the null was true? We square that, we divide it by the count we would have expected if the null was true, add them all up. And that's why it takes 1.5 years, because you are adding up these various pieces for every category that you've got, or every combination of categories that you've got. Once you have that chi-square statistic, then the computer will come up with a p-value. What's the probability if the null hypothesis is true, if there's nothing going on, that we see a difference or an association of this magnitude, a test statistic of this size, a sample like this. So the p-value, if the null is true, how often are we going to see sample data like this? Just by chance, not because there's anything going on, but just by chance. If there's a very low probability of seeing sample data like this, if the null is true, then we reject the null hypothesis. So that's why when the p-value is low, the null must go. The null must go. So we will be doing hypothesis testing, claiming there's nothing going on. The computer will compute the chi-square for us, will give us a p-value, and then we'll make a decision about our null hypothesis. The assumptions of the chi-square, as always, simple random sample. we need to have a simple random sample because we need a sample that is representative of the population in order to draw conclusions about the population from our sample. If we don't have a good sample, if we have a volunteer sample or something like that, all bets are off. There's no point in doing any inference because our sample is probably so unlike the population. We assume we have independent observations. That's probably true too. If we pick them at random, they're probably independent of each other. And then we also assume that we have at least 5 expected in every category or combination of categories. So we're not looking at the observed count in our sample. We need at least 5 expected if the null hypothesis is true. So chi-square, we're dealing only with categorical data. We're doing hypothesis testing. So we're making a claim about what's true in the population, that there is nothing going on versus something going on. The computer will give us the chi-square statistic and p-value, and then we'll make our decision.